So I'm really excited to tell you guys today about some of my research. A lot of this research that I'll tell you about was sort of part of my dissertation from University of Utah. And we'll tell you a little bit at the end about some of the stuff we're working on right now with respect to Columbia River Gorge pikas and responses to disturbance. So there are many signs that the climate is changing, and these include things like melting ice pack, raising temperatures, and changes in the distribution and type of precipitation that we see in many places. And climate scientists have really pretty good predictions about how a lot of these things are going to change in the future. But as ecologists, we're a lot more interested in how plants and animals may be responding to these changes in particularly temperature and distribution. Temperature and precipitation. So these are just a few of the species that have had documented changes in response to climate change. One you may not be aware of is a national treasure, the Easter bunny. And there are several species of lagomorphs that have responded in different ways to climate change. So while many scientists are interested in sort of weather forecasting and forecasting how exactly these abiotic factors are going to change, as an ecologist, I'm really interested in an ecological forecasting, which is really trying to understand where these different species are going to be able to persist in the future. One of the tools that ecologists commonly use to address these questions are niche models. And so just so that in case you aren't familiar with these, I wanted to kind of walk you through how niche models work. Typically, what we start with is a distribution of points of known occurrences where we know a species occurs. We can then map onto those known occurrences different layers of abiotic factors, things like humidity, temperature, or precipitation, and we can say this species is known to be found in areas that have these combination of abiotic factors. We can then basically come up with a map of current habitat suitability under current conditions, and then we can layer on how those changes in abiotic factors are likely to occur in order to determine future habitat suitability. And so in particular, basically this would allow us to predict areas where we might see a range expansion, where the species was not previously found but then will be found in the future, and areas of range contraction where the species was previously found but might be predicted to be vulnerable populations. So it turns out that these niche models are actually pretty good at incorporating abiotic factors, and we're pretty good at understanding how some of these abiotic factors are going to change across the landscape. But it gets a lot more complicated when we start to introduce ecological complexity. And one of the things that that niche models are really struggle with a little bit more is integrating things like species interactions. So these could be, interactions such as competitors or parasites, or what a species eats or what eats it, and also different aspects of microclimate, aspects of the physical environment that can help to basically buffer against the overall prevailing conditions of these abiotic factors. So this leaves us sort of with the persistent question of how are we able to identify habitats that can serve as refuges under continued climate change. And one of the things that I'm going to argue today is that we can actually learn a lot by trying to study species that are persisting in atypical habitats. So in particular, if we can understand how species are able to persist in an area that seems far too warm or far too dry for it under current conditions, this might allow us to identify fundamental habitat features that are necessary for that species' persistence under climate change. So in this case, of course, it's like beach balls and Ray-Bans that will allow marmots to persist on the beach. I'm really pleased, by the way, to inform you that I made this slide for a real talk. All right. So what I'm going to tell you about today, I'm going to give you guys a brief introduction to American pikas and tell you a little bit about why they're a sensitive indicator of climate change. I'm then going to tell you a little bit about pikas in atypical habitats, and the two types of habitats that I'm going to focus on in my talk today are pikas that are living in low elevations, like well outside of their predicted bioclimatic envelope that we would find from a niche model, and in habitats that have been recently disturbed. Finally, I'm going to sort of wrap up a little bit with trying to understand how we can use these data and studies like this to help us improve our ability to do ecological forecasting for climate change. So for those of you guys that were at my talk yesterday, you got a little bit of a small dose of Pika natural history, but I figured that more cute animal images nobody will complain about. So for anybody who hasn't heard, American pikas are these small mammals. They're closely related to rabbits, although they look a little bit more like a guinea pig. They're about the size and shape of a russet potato that you would get at the grocery store, and they typically live in high elevation rock slides across western North America. So the distribution of pikas is pretty restricted to these high elevation rock slides, and that distribution is thought to be limited by both a sensitivity to high temperatures and by a limited ability to disperse between patches of habitat. So together, unlike most alpine mammals, pikas are not able to hibernate. And so rather than, there's not a lot of things to eat during the winter, and they can't really go to sleep, put on fat stores and go to sleep. And so instead what they have to do is they have to invest in these really huge winter food caches that we call hay piles. So a single pika over the course of a summer makes a really significant behavioral investment in these hay piles. A single pika, again, about the size and shape of a potato, will collect on average across its range about 28 kilograms of plant material, which it will do over the course of about 13,000 hay trips. Just to put this in perspective for you, if we were all human pikas and we were making a hay pile for the winter, this would be the equivalent of amassing about 5,000 pounds of food for the winter, and each trip, basically it would be like going to the grocery store and carrying home 4 heads of lettuce in your mouth. So I encourage you the next time that you're at the grocery store, have a look at the potatoes a little bit more carefully and have a look at the big heads of lettuce and consider what it would be like to be a potato carrying home 4 heads of lettuce in your mouth. All right. Together, all of these factors have resulted in range declines in parts of the pika's range. And so this is a map that was redrawn from one of my collaborators' studies, Eric Beaver, who's worked extensively in the Great Basin. Each of these points represents a historical occurrence of pikas, so a place where we have historical evidence that pikas have occurred in the past. The blue dots represent places where pikas are still found, and the orange dots represent places where the population has gone locally extinct. And what we've seen is that at about 40% of these historical sites where pikas were previously found, they're no longer found. And those extinct sites tended to be in places that they had warmer summers in the talus and a reduced winter snowpack. One of the prevailing hypotheses as to why climate change might affect pikas in this region is that during the summer, the pikas are sensitive to heat, but they won't run around and be like, oh, I'm overheated, I'm dead. Instead, what they do is they restrict their activity and stay inactive below the rocks. And when they are inactive below the rocks, what they can't be doing is collecting that food for those winter hay piles. Similarly, during the winter, the snowpack actually acts like a layer of insulating, like a blanket over the talus, and helps to actually insulate the temperatures so that the temperatures that the pikas are actually exposed to in the talus tend to be right at freezing. So as you see these warmer summers, this equates to essentially a smaller hay pile for the pikas, and the reduced winter snowpack, particularly in the fall, means that the pikas may actually be exposed to colder temperatures during the winter. So given these constraints, this is the kind of habitat where we typically find pikas. Again, this is in the Wasatch Mountains near Mount Timpanogos. And we typically find pikas in habitat that looks like this, where there's a lot of rocks and ample meadow vegetation. In the Wasatch Mountains, this occurs between about 2,500 and 3,700 meters, so above about 8,000 feet in elevation. But where I've done most of my research on pikas in the Pacific Northwest, we find this kind of habitat on the big Cascade volcanoes, places like on the slopes of Mount Hood. So again, what you see here is like a nice big rocky slope with room for lots of pikas and ample meadow vegetation. In the Pacific Northwest, we tend to find pikas between elevations of about 900 to 1,700 meters, and that sort of is their kind of typical bioclimatic niche. But surprisingly, we also find pikas in some low elevation habitats such as the Columbia River Gorge, where pikas exist as low as 46 meters above sea level, and places, a climate that would be predicted to be unsuitable for the pikas based on what we know about their distribution and their relationship to climate. These are places where you have a long, hot summer and no snowpack to insulate the pikas against frequent freezing rain events. So one of the big questions that I set out to answer when I started studying pikas and I started graduate school in 2010 was trying to understand how are pikas able to persist in this atypical habitat. So the sections of the Columbia River Gorge where we find pikas tend to have a dense temperate rainforest characterized by lots of ferns and Douglas fir, and it's punctuated by these open rock slides that are one of the most notable features of these rock slides is this thick blanket of moss. This layer of moss can be up to about 6 inches or about 15 centimeters thick in many places, and it serves as a substrate for grasses, flowers, and ferns, sort of typical pika food resources to grow right on the talus. So one of the central questions of my dissertation was about how are pikas able to thrive in this atypical habitat. And with a team of undergraduates, I set out to collect a lot of hours of behavioral observations. So together we collected about 400 hours of behavioral observations of marked or known animals. And one of the notable things that we found is that many of the pikas that we were observing were actually consuming large quantities of this moss. So just as a side note, it took me about like 3 years to come up with this slide title. Get it? Okay. So at some of these sites, what we were finding is that these pikas, up to about 60% of their diet was actually made of moss. And in contrast, the sort of typical food resources that we would expect pikas to be eating, grasses and wildflowers, were less than about 30% of their diet. Now, this moss, basically nobody eats moss because it's got the nutritional composition essentially of like a cardboard box. But pikas are able to, we have some evidence that they may have special gut microbes that help them to be very efficient at extracting nutrients from this high fiber diet. And in addition, they're coprophagic, which just means that they send it through the system a couple of extra times in order to have some extra help from those microbes in fermenting the fiber. In addition, the moss essentially acts like a hay pile that is readily available, that releases the animals from having to forage off of the talus, and also is persistent throughout the winter, which may release them from having to invest in these big winter hay piles. And so indeed, when we actually went to look for hay piles, what we found is that actually only about 1 in 4 individuals in the Columbia River Gorge even bothered making a hay pile. And when we measured how much vegetation the ones that were caching collected, it was a tiny amount of plant material, about 1/5 the size of the hay piles that we see in typical habitats at high elevations. Another really important aspect of the moss and of the pika's ability to persist in this habitat has to do with the talus microclimates. So at each of these sites, I placed a big array of temperature sensors out in the rocks, and we collected data on the temperature at the surface of the talus, ambient temperatures as would be measured by weather stations, and the temperatures about 1 meter below the surface of the talus down in the interstitial space where the pikas are actually hanging out. So what we are looking at here is a time trace of temperature for about a couple of weeks in August of 2012 on the x-axis. On the y-axis, you're looking at the temperature in degrees Celsius. This yellow line represents the ambient temperatures that were collected at this site, and we've compared the readings from these ambient sensors to those collected by weather stations and found them to be really very similar. However, when we look at the temperatures measured in the talus interstices where the pikas actually live, what we find is a very different story. The temperatures at this particular site basically all summer remained about 6 degrees Celsius. And so just for your reference, that's basically like the temperature of a refrigerator. Indeed, we actually found, some of instantaneous temperature disparities between the ambient temperature and the temperature in the rocks of up to 31 degrees Celsius. And this is one of the biggest instantaneous temperature disparities of a microclimate that has ever actually been recorded. It far exceeds the average buffering capacity of most burrowing mammal burrow systems. So as far as how pikas are persisting in this atypical habitat, it seems like one of the really important things that they're doing is consuming an unusual food resource, maybe less nutritional, but it seems to release them from having to invest in hay piles and from having to forage very far off the talus where they may be sensitive to both higher temperatures and increased predation. In addition, they seem to be seeking refuge in favorable microclimates, and indeed the temperatures that we measured in the Columbia River Gorge were actually lower, so cooler and also more stable throughout the day than those that we measured in typical habitat on Mount Hood. So the next question that I sought to understand was what happens when a species habitat is disturbed? Do they need to go looking for new habitats, or are they able to stay and make the most of what's left after a disturbance? This is the part of the talk where I disclosed to you that I never sought out to study fire. So when I went and set up these field sites in 2011, I established a bunch of field sites in the Columbia Gorge, and for comparison, I was working at a couple of different places in typical habitat on Mount Hood. And one of those places was this lovely site, Pinnacle Ridge. This is a picture that I took on August 24th in 2011 when I was backpacking up on Pinnacle Ridge with one other field assistant. And 3 days later, that the whole north face of Mount Hood set on fire, with the Dollar Lake fire. And I actually didn't even know about this. I was on my way back home to Salt Lake City. I didn't read the Portland paper. I didn't hear about this fire until I came back in 2012 and discovered that all of my study sites had been completely incinerated. So the Dollar Lake fire burned actually almost the entire north face of Mount Hood, including left behind these sort of vast swaths of total destruction, complete canopy loss, and a really thick layer of white ashes left in many places. Many of you may already know this, but I came to learn that when white ashes are present after a fire, it indicates very, very hot fire temperatures, typically exceeding about 500 degrees Celsius. So this forest, encompassed all of these talus patches that had once been home to pikas, and indeed included many of the sites that I had been working at just the previous summer as sort of a control to my low elevation sites. So the first thing that I did is I sat down on the rocks and I just cried, and I was like, my thesis just went up on flames, literally, and I said I should just drop out of grad school. But I got some encouragement and some support from some really fabulous mentors and collaborators who helped me to understand that actually what had happened is that there had been a really nice natural experiment that had been created for me, and that we don't actually know all that much about how pikas might respond to wildfire because nobody's ever actually studied it. So they were like, you're really lucky. And I was like, I'm lucky. So together, we banded together and set out to answer some burning questions. I'm so funny. And those questions were, first off, could pikas even survive a wildfire? And secondly, how does this fire disturbance affect the habitat suitability for pikas? And then a more recent research question that I've been looking at is, what are the combined effects of disturbance in atypical habitats? So as far as whether pikas could survive a fire, I had been working at this Pinnacle Ridge site in 2011. I had trapped and marked 3 individual pikas here. And when I returned in 2012, you'll notice there's some really key changes about what happened at this site. So first of all, you'll see that the canopy cover over here in 2011 was completely gone. There was this big lush row of shrubs right here, and in 2012 when I returned, again, these shrubs had been burned into white ashes. So again, representing really, really hot temperatures. In many places, what moss cover there was on this site was really charred and darkened. But what you might not be able to see in this picture is my undergraduate students who are marking the location of our temperature sensors. So everybody always asks me, this is a really crappy picture. Can you fix this and make it look nicer? And I'm like, no, because I took that picture to be able to find those sensors again, not as a fire comparison. And so if I had known this would happen, I would have taken a much better picture. All right, so when we returned in July of 2012, we went back to these locations for these temperature sensors, and to my surprise, not only were the temperatures not, melted, but they also had appeared to have been completely functional and still recording data. So we eagerly grabbed the sensors, ran down to an internet cafe in Hood River and downloaded the data, and this is what we saw. So what you're looking at here is another plot of time trace of temperatures. On the x-axis, you've got date ranging from August 21st to September 20th, and on the y-axis, you're looking at temperatures measured by the sensors. The solid line represents the sensor that was at the surface of the talus, shielded from solar radiation by rocks, and the dotted line represents the sensor that was down about a meter into the talus interstitial space. So I looked at this and I was like, there was a fire. There's no fire. There was this row of shrubs that used to be there, and it's gone. And so I was able to dig around on the fire incident management website, and I was able to find an information in a fire progression map, which showed me that the fire actually reached this site somewhere early in the morning on September 11th. And it burned, that area was a source of heat until about midday on September 14th. And so what you'll notice from this graph is that this is when the fire was at this site, and the temperatures that we measured at the surface are not really that elevated. I mean, you have this kind of weird little spike right here, but the daily maxima that we recorded on this sensor are really well within the range of daily maxima that we saw prior to the fire. In addition, the talus temperatures are definitely a little bit elevated, but they still were well below our best index of acute heat stress in pikas, which is closer to about 25.5 degrees. Just in case you've forgotten, I just want to remind you that these sensors are about 20 feet away from a big row of white ashes. So 500 degrees Celsius here, 20 degrees Celsius right here. So I was really impressed by this in terms of looking at that at least with respect to temperature, we think that there's a lot of good evidence that pikas could have survived the fire. Unfortunately, at this site, I never recited any of my marked individuals, but it's really difficult to say whether or not they may have dispersed elsewhere or if they may have actually survived the fire, but then their hay piles burned in many cases, and they might not have had anything to eat over the winter. So that still is a big outstanding question. When we returned in 2012, the next step here was really to understand how this fire disturbance might affect habitat suitability for pikas. So you might imagine that between this burned site and an unburned site, there's a number of key differences. One of the things that we were really interested in understanding was whether the fire might have affected microclimate in the site. And so the talus really did a good job of buffering the pikas against the warm temperatures of the fire, but following the fire, you might imagine that it could be much warmer at this site as a result of both losing the canopy cover that provides shade to the talus, and also perhaps changes in the albedo or the surface reflectance of these rocks as a result of all of the char and the burned moss. So we set out to survey a number of different sites. At each site, we conducted a couple of different kinds of surveys in order to classify the burn severity. So all of these sites were roughly north-facing. We selected a number of unburned sites that had no evidence of fire within about 25 meters of the perimeter of the rock slide. And then we selected a number of sites that were within the perimeter of the fire, and we distinguished between the moderately burned and the severely burned sites based on both the percent of the canopy cover that was lost in the fire and also the percent of the linear patch perimeter that was burned in the fire. Importantly, we found that there was no difference in patch size between these categories of sites, suggesting that the fire had not preferentially burned sites that were smaller or larger. And all of these sites, I either had been to before and knew that they were occupied, or they had evidence of previous pika occupancy, such as scat, which indicates that pikas were present at least in the last 4 or 5 years. So for the purpose of this microclimate analysis, I lumped the unburned and the moderately burned sites together. The reason that I did that was that at the moderately burned sites, there was relatively low percent of loss of canopy around the rock slide and relatively little evidence of charring on the rocks. So at each of these sites, I placed a temperature sensor at the site near the surface of the talus, but shielded from incident radiation. And we used the data that we collected at these sites to calculate several different metrics of thermal stress in pikas. So you might imagine that heat stress, so the temperatures being too hot, could act either acutely on pikas through basically the number of very hot days, or more chronically over a longer period of time, which we use to index by the average temperature in August. And these are metrics of thermal stress that have been predictive of habitat suitability for pikas in previous studies. Cold stress could also act like acutely or chronically, so we use these data to calculate the same thing for acute cold stress and for chronic cold stress. In the interest of time today, I'm only going to show you data for the metrics of acute heat stress and acute cold stress, but know that the chronic metrics of heat and cold stress showed the same pattern that we saw in the acute. So you might imagine that each of these metrics of stress in pikas would vary with elevation. So on the x-axis here, you're looking at elevation in meters. On the y-axis, you're looking at the number of very hot days. And for anybody who has traveled into the mountains up to Beaver Mountain, you would know that as you go up in elevation, the number of very hot days would get colder. And indeed, we did find a pattern where the number of very hot days decreased as you went up in elevation, but importantly, we found no difference between the severely burned versus the unburned and moderately burned sites in this analysis, suggesting that the severely burned sites did not experience increased acute heat stress more than what you would predict based on its elevation. So we did the same thing with cold stress, and you might expect similarly for cold stress to vary with elevation. And now this graph may seem a little bit counterintuitive because it gets colder as you go up in elevation, but remember that this snowpack actually acts as like a blanket or a layer of insulation for pikas. So you might expect to see a reduced winter snowpack at lower elevations, and as a result of having less winter snowpack, you then might expect to see more very cold days down in the talus where the pikas actually live. And again, this is what we found, a strong trend for decreasing acute cold stress as you go up in elevation, but again, that these severely burned sites did not experience more cold stress than we would predict based on their elevation. So we found very little evidence that the fire affected the microclimates that were important for pikas at these sites in the years following the fire. However, the microclimate is only one aspect of habitat suitability. And, of course, another very important aspect has to do with food availability. To try and understand how food availability might affect habitat suitability for pikas, we conducted abundance surveys with the idea that the number of animals at each site might be more illustrative as far as the suitability of the habitat than whether or not the site was occupied or unoccupied. To conduct these surveys, we walked transects across the length of the talus, and we recorded any locations where we saw pikas or we heard their calls. We also noted signs like fresh hay piles or fresh clippings under the rocks as unequivocal evidence of current pika occupancy. And again, with the idea that abundance might be a more sensitive indicator of habitat suitability than occupancy. At each site, we also conducted vegetation surveys, and we did so non-destructively so that we could do repeated sampling. And so at each of these sites, we established randomly 5 1-meter square quadrats around the perimeter of the talus, and we revisited these quadrats in the spring and the fall of each sampling period, and we estimated, basically the biomass of plant material and also the abundance of each species within the quadrat so that we could observe this recolonization process. I harnessed the remarkable renewable energy source of middle schoolers in some of this work. I mentioned yesterday in my talk that I collaborated with a school in Salem, Oregon, and this was a collaboration with a school called Jane Goodall Environmental Middle School. And they call themselves JGEMs. At JGEMs, all 8th grade students have to conduct an original field research project. And so what we did is that we worked with these students to collect the same data that I was collecting more broadly in this study at 3 different study sites: a severely burned site, an unburned site, and a moderately burned site. We taught the kids how to operate the temperature sensors and place them in the rocks, how to survey for pikas, and how to conduct the vegetation survey. And then these three sites served as the basis for their independent research project, but also contributed more broadly to our project. This project is still ongoing, so the teachers at JGEMS are still taking 8th grade students out to these same 3 sites on Mount Hood and continuing to monitor the recovery. So indeed, we did find that there were fewer pikas at these severely burned sites. So what you're looking at here is the sampling season, year and season, and on the y-axis you're looking at the average number of pikas that we had detected at each site. What you can see is that across all seasons and years we found a lower abundance of pikas at these severely burned sites. And when we looked into predictors of abundance, one of the strongest predictors, far more so than fire severity metrics, was vegetation. This is a little bit of a complicated graph, but I'm going to walk you through it. What you're looking at here on the x-axis is the vegetation biomass, the average vegetation biomass in those 5 1-meter square quadrats, and the y-axis is the number of pikas that we detected. Each of these points represents one site in one season of sampling, and the shape of that point represents the sampling period in which the data were collected, and the color of it represents the burn severity status. What I found really stood out to me about when I first looked at this graph was that there seems to be kind of a vegetation threshold here at about 55 grams per meter squared. If we look above that vegetation threshold, what you find is that there's really not much of an effect of vegetation abundance on the number of pikas that we detected at that site. And in contrast, when you look below this threshold, what you see is that there are very few sites that have more than a single animal at it, which would be necessary for a reproducing population. Just to give you a feel for what this might look like, this middle picture here is a quadrat that is right at that threshold of 55 grams per meter squared. Many quadrats had much less than that, and of course some of them had much more than that, particularly at the unburned sites. So again, unfortunately we can't say conclusively, but the widespread distribution of pikas following the fire and the fact that every single one of our sampling sites was occupied in at least one season following the fire really suggests that pikas may have been able to survive the fire, and particularly because those microclimates remained so cool that we measured during the fire. Following the fire, it seems that the severely burned sites were not more thermally stressful, and pikas were able to quickly recolonize areas once the vegetation had recovered to approximately that threshold. Now, many of you guys may be sitting there waiting to ask, Dr. Varner, didn't the Columbia River Gorge also burn up recently? And the answer to your question is yes. So last fall in September of 2017, there was a fire started by a kid with throwing fireworks off of a trail in the Columbia River Gorge, ignited this massive, massive wildfire, the Eagle Creek Fire. And the Eagle Creek Fire burned for several months in the Columbia River Gorge and basically burned the entire distribution of pikas in this unique low elevation habitat across, on the Oregon side of the Columbia River Gorge. When I actually had a trip out there in early November that I had planned anyway, just to service my temperature sensors that I have been maintaining out there, and so I called up the Columbia River Gorge National Scenic Area and the Forest Service, and I pleaded with them, since the fire was no longer near my sites, to please let me in so that I could get my temperature sensors and also survey for pikas, because one of the things that we weren't able to do with the Dollar Lake fire was get in right after the fire to be able to say that pikas conclusively survived the fire but then didn't make it over the winter, etc. But unfortunately they had not been able to get in there and actually do very much of the risk assessment, and there was still a lot of pretty serious hazards, including but not limited to mudslides, falling rocks, and falling trees. And they decided that it probably wasn't safe, and so I spent that trip instead drinking wine with my family and crawling around roads of Cascade Locks with my binoculars, trying to catch a glimpse of my sites status and find out exactly what had happened to them. We were able to actually get back in early in June of this past summer. And so when I got back to many of these sites, I discovered that at least at some of them, the fire had had a pretty extreme impact, particularly on this thick layer of moss. Many places there wasn't nearly as much canopy cover loss as there was on the Mount Hood fire, but there were a lot of places where this thick layer of moss on which the pikas appeared to depend really heavily was almost entirely lost. Furthermore, some of my temperature sensors didn't fare quite so well this time around, and so although I wasn't actually able to measure the surface temperatures during the fire of this sensor, we can conclude that it was at least the melting point of this plastic. So I'm still trying to get somebody at Hobo to see if they can get anything out of this. Haven't had very much success, but I'm working on it. Luckily, my talus sensors did survive the fire, and so this particular site, this is what my surface sensor looked like. It was placed right here, and during the fire, or sort of just before the fire, we see this was this really characteristic situation where the temperatures are really low, really stable throughout the day. When the fire reached that site near September 14th, we saw a really sharp increase in temperatures a meter below the surface, up to a whopping 7 degrees Celsius, which is still well within, by the way, the range of a working refrigerator. Your food will not spoil at that temperature. So, so impressively, the temperatures during the Eagle Creek fire also really remained cool, in spite of the fact that my surface sensor was melting just a few feet away. So for me, this really sort of reiterated that this importance of this thermal buffering capacity of the talus. And just as sort of a fun fact, I now am both the first and the second person ever to have measured temperatures in a rock slide during a wildfire. So I got that going for me. As far as pika abundance goes, we received a grant from the Citizen Science Competitive Funding Program at the U.S. Forest Service. They went into their first year in 2018, and we were selected as one of about 10 different projects that they funded to be able to engage citizen scientists in helping us to monitor post-fire pika abundance in the Columbia Gorge, at least in the places that were open to the public this summer. So in June of 2018, I returned to the Columbia Gorge, and I conducted 5 4-hour trainings with 8 groups of citizen, 8 citizen scientists in each training. My jokes got funnier every time. That was a joke. and what we train them to do is to conduct standardized surveys, as we had on Mount Hood, to be able to count the pikas, estimate their abundance, and to collect some burn severity and habitat data. So these include metrics of how much moss was lost, what was the canopy cover loss, and evidence of the linear patch perimeter that was burned. We also asked volunteers to record information about the survey conditions, so when they went, what time of day, what time of year, and also how many minutes they spent surveying and what kinds of evidences they found. And we sent them out with a team leader. Typically the team leader was somebody who was a professional scientist in some capacity or an experienced volunteer who had conducted these surveys with one of us before. These volunteers were able to survey 36 sites in 2018, and for at least 12 of those sites, we asked multiple teams to visit the same site in order to look a little bit at data quality control and at detectability. So previous to the fire of those 36 sites, prior to the fire, 84% of those sites were occupied. It was a pretty high occupancy rate following the fire, or before the fire. Following the fire, we did see a big sharp decline in pika occupancy, down to about 44%. And specifically what we found is that 16 of the sites that were occupied prior to the fire were no longer occupied after the fire. However, we did find that 2 sites that were unoccupied prior to the fire appeared to have been colonized by pikas in the intervening year. And these were both sites that were very small patches of talus, but sites that had a really high percentage of unburned moss cover, suggesting that following the disturbance, some of those previously less suitable habitats were becoming more suitable as a result of being less disturbed. When we looked at the inconsistencies in resurveys, this was kind of an important learning experience for us. Again, we sent volunteers to two different independent sets of volunteers to 12 different sites. 7 of those sites that they went to, we found consistent results between the volunteers where either both teams found it to be unoccupied or both teams found it to be occupied. However, 5 of those results were inconsistent. When I started looking into what might explain these inconsistencies, the biggest predictor was that I had one team leader who was responsible for 4 of these inconsistencies, where in 4 of these situations in these 4 sites, the other team had found pikas and this one particular team leader had not found pikas. And so this really highlighted for us the need for a little bit better quality control and a little bit more intensive training for our team leaders. The other thing that really strongly predicted whether volunteers were going to find pikas in these detectability surveys was the minutes that they spent surveying. So you're looking here at the minutes spent surveying. These points of the 0 represent that pikas were not detected, and the 1 represents that they were detected, and this line represents the modeled probability of detection. And what we see is that there's sort of a sharp increase that if pikas are present at the site, that you're much more likely to detect them from having surveyed over 50 minutes. So this led us to a couple of important lessons in terms of how to improve data quality and training for next year. The grant luckily is 2 years long, and we'll be going out and doing this again next year. Biggest thing is going to be vetting of team leaders and trying to make sure that the team leaders receive a little bit of extra special training in terms of how to keep a close eye on their volunteers that they're overseeing. We're also thinking about establishing a minimum survey effort of 50 minutes and establishing some kind of protocol for follow-up surveys whenever a team fails to detect pikas at a site. And this is one of the big challenges that I mentioned about engaging citizen scientists in this kind of work yesterday, which is that very few people want to go and spend 2 hours really meticulously surveying a site and then not find the pikas. Everybody wants to go to a site and find the pikas right away. So trying to deal with this absence information is a big challenge for us. So together this work I think has a couple of really important implications. Again, both of these studies have highlighted the importance of talus as a thermal refuge, particularly during wildfire for pikas, but also probably for other small animals that need to seek some sort of refuge during the wildfire. That vegetation threshold has some important conservation implications because it gives us some idea of basically the minimum amount of vegetation that might be necessary to sustain a reproducing population of pikas. And our experience with citizen scientists has really helped us to develop a practical set of guidelines for being able to implement citizen science monitoring following a disturbance like this for this species. So I'm going to wrap up my talk today by trying to talk a little bit about how we might be able to improve ecological forecasting for climate change and what kinds of lessons this work has given us in this sort of big field. The first thing is that it seems like it's really important to be able to identify habitat features that might buffer microclimates from the prevailing conditions in the ambient temperatures. And in both of these habitats, both the low elevation habitat and the disturbed habitat, there were several different conditions or habitat features that really helped to buffer those microclimates. The first is a thick forest canopy cover in the low elevation habitat that might reduce the amount of incident sunlight that is actually affecting the microclimates in the talus. Both sites were in the Pacific Northwest where we see high humidity and high precipitation, and indeed both of these conditions have been linked to increased dispersal ability in this species. The third is this thick layer of moss, which may serve as both a food resource and also in an evaporative cooling capacity, helping to actually cool the microclimates in the rocks. And finally, there is also some strong evidence that at least in the Columbia River Gorge, there may be some sort of subsurface water or ice feature, in particular at some of these sites where the moss cover burned, but the talus temperatures really remained quite low even during that fire. I think another sort of implication of this work, and particularly of, for example, the vegetation threshold analysis, is this importance of being able to include species interactions such as food quality and food abundance in these kinds of models. And then finally, I think that this work highlights the importance of being able to select climate data at an appropriate scale. So a lot of times, a lot of ecological modeling papers will select modeled climate data or climate data from weather stations. And what this work really suggests is that it's really important to take into account both the spatial variation in climate and the size and mobility of the organism in question when selecting that climate data. So, for example, if you're modeling climate for some large immobile, organisms such as these big old growth trees, you might be able to use different climate data than a small animal that's able to rapidly shuttle between these really heterogeneous microclimates. And this leads to one of the big outstanding questions in the field, and one of the things that I am trying to address with some of these long-term climate data sets is how will these really small-scale microclimates, such as the temperatures that we measure down below the rocks, change as a result of changes in ambient prevailing conditions. So stay tuned for that. We're starting to get to the point where we might be able to answer some of those questions, having 8 to 10 years worth of data at some of these sites. And the advent of small, cheap temperature sensors is really also helping to facilitate research in this field. So with that, I have many, many people to thank, but particularly my collaborators and mentors, field assistants, and particularly J.J. Horns and Mallory Lambert. These guys, I injured my ankle really badly in 2012 during the middle of field season, and not only did they perform an emergency rescue, carrying me out of the field site about 5 miles, but they also, just really stepped into leadership roles on the field crew and enabled data collection to continue uninterrupted. And then, of course, all of these wonderful organizations who I've convinced to pay me to go hiking and watch cute animals over the course of the last 10 years. And with that, I would be totally happy to answer any questions that you may have. It looks like we've got about 10 minutes. Yes?
Is there any data on how big the range is for an individual pika? So over winter, even though the temperatures don't get, or during a fire they don't get too hot,
yeah.
I think they may have survived. It seems like they'd have to probably travel out of the fire boundary actually to be able to survive over the winter.
Right. Yeah, so the question was about data on home range size in the pikas and how far they actually travel, and that in many of these disturbed habitats, they may have to travel really far away. I think you're absolutely right. We did try to measure home range size of pikas in the Columbia Gorge versus Mount Hood. We found that in the Columbia River Gorge, they had very small home ranges, and so they were typically very localized and probably as a result of the abundance of food resources, but I'm sure that that has probably changed as a result of the fire. We never actually measured home range size in the disturbed areas of Mount Hood, but I can tell you that there are a couple of sites where, for example, one thing that happened was that my field assistant was out and she was like, I heard a pika, and we were at this burned site where there was literally one elderberry bush that animal could, that was green around the entire rock site, and I was like, I'll be the boss of deciding whether or not you heard a pika, because I don't think there are any pikas here, because it would be crazy if they were here because there's nothing to eat. And so I went over to where she was, and sure enough there was a pika there, and I was just like, what are you eating? So I think that you're right that there has got to be some, larger use of space, especially in those really low food abundance habitats. Yeah. Does that answer your question? Okay. Yes?
I'm really sorry, I have a cold.
No problem. Me too. That's why I'm on the mic.
I was just curious, how long does it take for those patches of moss to grow back to a place where they can sustain populations? Does it take a long time to grow back?
So the short answer to the question, how long does it take for moss to grow back, is I don't know in this habitat. The longer answer is that many people have shown that mosses are among the slowest growing plants, and that my guess is that it will be decades before those mosses grow back to how they were before. The big question that we're trying to understand is, like, to what degree do the pikas depend on the moss? Because my previous research suggests that they were really making use of it to eat it, and that it may have had an effect on the microclimates that they were experiencing. But it may be that the moss is able to rebound to an ability where it can sustain other plants growing out of the talus, and then the pikas can eat those things while the moss is recovering, on a relatively fast time scale. I don't know, and we're hoping to try and get at that as well. Yeah.
I'm wondering if you know throughout the entire range of the pika, what portion of their range is represented by the alpine sites, like in the Sierra Nevada or the Rockies, versus these lower elevation sites that you've been talking about?
Yeah. So the low elevation sites are definitely the exception, not the rule. A much higher percent of the pika's range is in the higher elevation alpine sites, although they are found in several other sort of like atypical or unusual places, including lava beds and Craters of the Moon National Monument in Idaho. So if you drive north of here like an hour up into southern Idaho, there's like this big, lava flow up there, and it's super hot and it's super dry, and there are pikas there everywhere, and it's really weird. And so that's another place where I've been working a little bit with some collaborators at Washington State, trying to understand how the pikas are living there. But definitely across their range, they're much more frequently found in the alpine and less frequently found in these lower elevation places. And it seems like they're found in the lower elevation places when there is a suitable microclimate that like helps to buffer against the ambient conditions, and in these places where there's like some sort of suitable food resource that is able to sustain them without them having to forage like crazy like they do in the alpine. Yeah. Yes.
Aside from fire, is there any other disturbances that have a big effect on pika?
Yeah, so there have been people who have tried to look at grazing disturbance and its effect on pika, but the thing is that there's not actually that many places where pikas and cows overlap because most of the places where pikas live is not really a particularly suitable place for grazing cattle. And so in that sense, they tend to be a little bit more protected from, the typical anthropogenic disturbances. And certainly habitat fragmentation isn't really a problem because their habitat is by definition fragmented, and it's not getting worse with human activities. So, yeah.
Is there evidence of lower density in populations on the lower elevation sites?
Yeah, so I think that there's evidence, like at least in the Great Basin, of lower density populations in the lower elevation sites, but there's not, particularly like in the Columbia River Gorge before the fire, they actually had much higher pika densities than anywhere that has ever been measured before ever. So I don't think it's necessarily straight up correlated with elevation, but probably more so with resource availability. That would be my guess. Yeah. Is there one more? Somebody over here? Sure.
On the question of density, you're looking at population abundance.
Uh-huh.
Yesterday you talked about how there was acoustic stuff they're using.
Yeah.
And the type signature is defined. You're looking at different dialects maybe.
Yeah.
Is there a promise that you can even do that down to individuals?
Yeah, so the question is about, can we detect individuals by their call frequency? The short answer is I don't know, but the longer answer is that I think maybe for some individuals, but probably not most individuals. So in my brief experience with watching marked animals that I know for sure are marked, I think that there is probably more variation within a single animal's vocal repertoire than there is between animals. But there are animals that we can identify with their call. So for example, we had one animal in the Columbia Gorge during my behavior study there that we nicknamed Scratchy because it had this like weird like scratchy call. And it only ever made that call and nobody else made a call that sounded like that. So for that animal, I feel confident that my engineers would be able to detect the difference between him and somebody else. But for the rest of them, I don't know. Yeah. Yes?
So the little bit that I know about pikas is that they're a conservation concern because of limited dispersal with climate change. Things are getting warmer and they're not like that.
Yeah.
But with the buffering capacity of the talus, it seems like things would have to get a lot warmer before that would really render them, incapacitated at those sites.
Yeah.
And it seems like your research with the moss at the lower elevations is kind of optimistic in terms of their adaptive capacity. So I was wondering if you could talk a little bit about how your research informs climate change.
Yeah, so, I mean, I think you're right that certainly we can learn about their adaptive capacity with respect to the moss, and particularly with respect to dietary plasticity. Like, I think that to me suggests that, like, if you can eat moss, like, you can probably eat pretty much anything as long as it's not, like, specializing on one class of super nasty toxins. And even then, I don't know, maybe they get some gut microbes from pack rats or something. And so I think that certainly they have a wider range of dietary plasticity than we might have expected before. With respect to the buffering capacity of the talus, I think that what we see in the Columbia River Gorge is really unusual. So I've measured temperatures at Craters of the Moon National Monument and at in the Uintas and in the Wasatch and in Colorado and in Mount Hood, which is not to say everywhere, but a lot of places. And the Columbia Gorge is the only place that you see that, like, flat line talus temperature pretty constant. And that to me suggests that not so much that it's about the pikas and their resilience, but about the, like, uniqueness of that habitat as, like, a refugial kind of place. And so I think that trying to understand, exactly in some of these low elevation habitats, is it because the habitat is a special place, or is it because the pikas have adapted to that habitat, is kind of the key question. And at least with respect to the Columbia Gorge, before the fire, it seemed to me like it was really about sort of the specialness of that habitat. Although certainly there's the adaptive capacity issue with the diet. So it's a little bit of both. Does that make sense? So I think that one of where you start to see the species getting more sensitive and running into trouble is in places where that buffering capacity, that habitat is not so good, and they aren't able to basically compensate for it by hiding under the rocks and eating some unusual food resource. So I don't want to keep you guys past 5, but if anybody else has questions about pikas, I'd be happy to take them down here. Thank you again for being here and for your attention and for making this a really lovely visit.